Hello everybody, this is Dr. Christopher White, and in this video we're going to be looking at the lab exercise correlation. So one of the problems that geologists have to deal with is that a significant proportion of the rocks that constitute the Earth's surface are not accessible to geologists. Now this is because they are covered by a layer of unconsolidated sediment which is referred to as cover. And this veneer of sediment is going to be somewhere between 1 and 600 meters in thickness. Now, already, some of you have probably already thought to yourself, hold on a second, I know that there are parts of the world where you have extremely thick sequences of sediment which will measure in the thousands of meters, so that statement doesn't make sense. But when we're talking about cover, what we are dealing with is unconsolidated sediment. Once you get below about 600 meters, the sediment is being compacted already, and it's being turned into a more solid material. In fact, it's in the early stages of the lithification process. So that's the difference we're dealing with here. Now, obviously, because these rocks are not accessible to geologists, it makes it very, very difficult to link the strata from one location to another. I mean, if there was no cover, you would just simply be able to walk between the two locations and carefully mark out what's happening to the rocks. However, that's not something you can actually do. So instead, what geologists have to do is we have to visit whatever locations we have available, and we have to analyze those outcrops. So we've already we'll look at the rocks that are there, the fossils that are there, the order of the rocks, the relative age of the rocks, if possible, the numerical age of the rocks, and we will use that to produce a stratigraphic column for each of the locations which we visit. So then what we're going to do is we are then going to use these stratigraphic columns to make educated predictions about what is happening to the geology in between them. Because remember, we cannot see that geology because it is not accessible to us. And this is the basis of the process of correlation, which is the mechanism we use, or the methods we use, should I say, to link rocks from different locations together and to predict what is happening to them between the locations. So the most commonly used method of correlation is physical correlation, and there's several ways that you can do this. So the first way is to look for lithological similarities or marker beds between your locations. So what you're going to look for is you're going to look for a layer which has some kind of distinctive appearance. And this is normally due to the fact that these beds have a different origin to the rest of the beds which make up the sequence. So for instance, it might be something like a bed of volcanic rocks within an otherwise sedimentary sequence. So obviously, because it's a distinct unit, it may have a difference in color. If it's a sedimentary rock, it could have very distinctive sedimentary structures, or it could have very distinctive fossils, or there could be some kind of change in mineralogy, which makes it, completely distinct from all the other rocks in the unit. Now, the nice thing about finding a marker bed is that it's very easy to spot when you move from one location to another, and so you can link locations relatively quickly and relatively easily because this bed is so distinctive. So a classic example of something that could be used is something like a black limestone layer, or like I said, it could be a layer of volcanic rock in an otherwise sedimentary sequence. So the next thing you can do is you can look at the sequence of beds themselves. So sedimentary and volcanic sequences will often display the same lithologies repeated multiple times. So if you just think of a standard sedimentary sequence, it's not uncommon to find multiple layers of sandstone and mudstone as part of the same sequence. And of course, the problem is that in most cases, one layer of sandstone looks just like another layer of sandstone. So it can sometimes be very difficult to actually, link those beds together between different locations. However, if you look at the total package and actually note the sequence in which the beds occur, you can then apply that sequence to the next location. You can see, right, does this sequence of beds occur at the second location? Yes, it does. Where does it occur? Great. I now know that that package of rock can then be correlated to the package of rock at the original location where I started. Now, something else that we can look at are sedimentary sequences with regard to cycles. So, analysis of sedimentary rocks in the geologic record has demonstrated that there are cycles which occur. And these cycles have a period of between 20,000 years and 150 million years. I do apologize. And they will often be superimposed upon one another. So that means obviously the larger cycle will have multiple smaller cycles within it. Now, the reason for these cycles is most likely a result of changes in the amount of solar energy received by the Earth. And so these changes will be primarily due to the Earth's wobble, because of course as the Earth rotates, it actually wobbles around its axis, and over a long period of time this wobble will actually cause the angle at which the planet faces the sun to change. There are also variations around to do with the Earth's orbit as it moves around the sun. Sometimes the Earth's orbit is more circular, sometimes it's more elliptical. And so these variations will result in the amount of solar energy received by the Earth changing, or should I say it will change the amount of solar energy received by certain parts of the Earth's surface changing. And so what this means is that if conditions are right, you will end up with one of the poles getting very cold because it will be receiving less solar radiation. When this happens, obviously, the temperature at that polar region will decrease, and that will therefore allow it to build up more and more ice and snow. And so this will obviously eventually lead to the formation of large glaciers. These large glaciers will then start to lock up seawater, or more accurately, you'll lock up the water that's dropped as snow, which came from the evaporation of seawater. And this will steadily cause sea levels to drop. Eventually, variation in the Earth's wobble and in the Earth's orbit will cause the polar region to begin warming back up again as it receives more solar radiation, and that water will then exit, so the glacial ice will melt, and then it will return to the ocean basins, causing the sea level to rise. And so these variations caused by changes in the Earth's orbit and its wobble are often referred to as Milankovitch cycles. Even though these cycles are very, very common, what we can do is we can look at the length of each cycle, and we can look at, these cycles within a sequence. So we can say, right, we've got a long cycle followed by a short cycle, followed by a medium, followed by a long, etc. And so what we can then do is we can then use this to link rocks between different locations, because we can look for the same sequence of cycles within our sequence of sedimentary rocks. Now, this is obviously because these changes in sea levels will lead to transgressions and regressions, so sea level rise and sea level retreat. And so this is obviously going to change the rocks that we see within our package. So by looking at these packages of rocks, we can say, right, we've got a cycle here, followed by another cycle, followed by another cycle, and then we can look for the same thing at the next location, and then we can link them together using the cycles. And the nice thing about this is that it works because these cycles are going to be contemporaneous, because we're talking about global sea level change here. So you can not only use this technique on a local or regional scale, in some cases you can actually apply it on a near global scale. So you can look at deposits, let's say on the east coast of North America, and you can compare them to deposits on the western side of Europe, and you can link them together using these cycles. And so this is the basis of the geologic process, which is referred to as sequence stratigraphy. So this is simply using these sequences of rocks, which are related to transgressions and regressions, to link locations, sometimes over extremely large distances. The final method of physical correlation that we can use is geophysics. So although you're probably thinking, how does geophysics allow you to physically correlate individual layers of rock? The methods that we're about to discuss actually do allow you to pick out individual layers or individual packages of rock, which can then be linked from one location to another. Now, the vast majority of the time when we are talking about geophysical data, we are talking about it in the context of a down borehole survey. So what's typically happened is you have two locations and they've been drilled by an oil and gas company, or maybe a mining company, or an environmental company who's maybe doing something like a groundwater survey. And so then what they'll do is they'll pass down geophysical tools down the boreholes, and they will measure the properties of the rocks that they pass by. And so what we're going to look at now is we're going to discuss some of the things that can be monitored as these down borehole tools are passed down the borehole. And this information can then be used to link layers of rock from one location to another. Now, the final thing is that it can't give you a definitive piece of data about an individual layer of rock. What it's going to give you is the sequence of rock. So it'll be able to tell you, right, this is a sandstone, mudstone, sandstone, limestone. So you'll have that entire sequence mapped out for you, logged for you by these methods. And then what you can do is you can then look for the matching sequence at the next location, and then that will allow you to correlate the layers of rock from location 1 to location 2. First method is resistivity, and this method will measure how easily a layer of rock will conduct an electric current. So how easily will that electricity move through the layer of rock? Now, the first thing you need to remember is that this is a comparative resistivity. So it's, they'll compare the resistivity of the sandstones, the limestones, the mudstones, and any other rock that's there. And you'll just see, one of the rocks will have the highest resistivity, one of the rocks will have the lowest resistivity, and the other rocks will be somewhere in between. But you can use that comparative resistivity to work out, am I looking at a sandstone, a mudstone, a limestone, etc. So in the case of sandstones and limestones, they have quite a high resistivity, so the electric current has difficulty passing through them. In contrast, mudstones have quite a low resistivity, comparatively speaking, so they will conduct an electric current far more efficiently than a sandstone or a limestone. So if you were to look at a graph, you would see every time you went through a mudstone layer, you would see the resistivity decrease, whereas every time you looked at a sandstone or limestone layer, you would see the resistivity increase. Now, there is one slight issue with resistivity, and that's because sandstones and limestones are typically relatively porous rocks when compared to mudstones. And typically, these rocks are several hundred meters, maybe thousands of meters under the surface of the earth, and they're typically filled with a salty brine in the pores. And the salty brine will actually conduct electricity very efficiently. So if your sandstone or limestone contains quite a lot of salty brine within it, you will see the resistivity will drop because the electric current can move through it more easily. So there is a little variation that can take place with the addition of certain fluids in the pore spaces of your rock, but geophysicists expect this and they know how to account for it. So the next method is going to be spectral gamma. And so this method will measure the intensity of gamma rays, so radiation, released by a layer of rock. So different sedimentary rocks will contain different amounts of radioactive isotopes. They'll be contained within certain minerals. So a mineral like zircon would be a classic example. When your rock has a higher concentration of these radioactive isotopes within it, obviously you are going to produce more gamma rays as a byproduct of radioactive decay, and the gamma ray spectrometer will pick it up as it moves down through the borehole. So once again, this is going to be a comparative analysis. So you're just going to compare the amount of gamma rays being released by the sandstones versus the mudstones versus the limestones. So sandstones will typically present elevated rates of gamma ray production relative to limestone. And this is because sandstones will often contain minerals that have some uranium or thorium within them. So we're looking at minerals like zircon or apatite, which is calcium phosphate, or a whole range of rare earth element phosphate minerals, things like monazite. And of course, the presence of these minerals will lead to, a slightly higher gamma ray release versus a limestone, which on the whole is relatively poor when it comes to minerals that contain radioactive isotopes. Now, mudstones, once again, are in a different situation. They will typically produce the highest amount of gamma rays. And this is because they are made up of clay minerals, and clay minerals are often quite potassium rich. And so the isotope potassium-40 is radioactive, And so given the large amounts of potassium contained within the minerals that make up the mudstone, you actually have quite a lot of radioactive isotopes within your mudstone layer. And so mudstones will typically produce higher gamma ray emissions versus a sandstone, and a sandstone will produce higher gamma ray emissions versus a limestone. So if we were to look at a plot of gamma ray emissions, we would see that limestones would be the lowest, then sandstones would probably be somewhere in the middle, and then mudstones would typically give the highest gamma ray levels. So the final method we can use is remnant magnetism, and this is just like the magnetism we've spoken about when we've been discussing things like divergent plate boundaries. It's all to do with how the iron minerals within the rock orientate themselves as the sediment is either being deposited or is being lithified into a rock. So when that's happening, obviously these iron minerals will align themselves parallel with the Earth's magnetic field at the time. And so if you remember, going back to plate tectonics, you get these bands where you have rocks which have a normal polarity, which is like the present day, and you have rocks that have reversed polarity, which is the reverse of the present day. And so what you can do is you can actually measure the remnant magnetism from the core that's pulled out of the ground. And as long as you know the orientation of the core, that's quite important. But you can measure the remnant magnetism of the rocks, and then you can compare the periods of normal and reverse magnetic polarity to essentially work out how old the sample is. And then you can also compare the remnant magnetism to other locations. So you can say, okay, we have a big period of normal polarity, then a short period of reverse polarity, then another big period of normal polarity. Can I see the same thing at the other location? And if you can, great. That means you can correlate those, that layer of rock or layers of rock together and say that they formed, they are the same layer. So those methods will lead to you being able to link distinct layers or packages of layers between locations. Now, geophysics also offers an additional method for looking at layering in the subsurface. So this is going to be seismic data, and we actually have an example of a seismic section over here on the right. So in the case of a seismic section, what it does is it allows you to view the lateral development of a stratigraphic sequence. So what's happening, as you go sideways from a point. So if you look at the seismic section at the top here, you will see that you can see distinct layering. So you can see this layer, for instance, is starting here. It comes all the way across the top and continues all the way to the other side. So you can see what's happening to that layer. In contrast, if we were to look at one of the layers down here, you'll notice that it terminates when it hits this area right here, and something going on there, probably a salt dome or something that's obscuring the layering. So what we have is a method that allows us to see a far more complete version of what is going on in the subsurface. So when we are producing a seismic section, how are we going to do that? Well, obviously we're going to need to produce seismic waves. And if you're on land, this will be done either using explosives. So you'll set off an explosion, which will produce seismic waves that go down into the ground. Or you will use vibrating plates, which are attached to large trucks, and they will be pushed to the ground and vibrated. And the vibrations produced also will send seismic waves into the rock. Now, when it comes to doing this kind of survey in the ocean, you are going to use shots of compressed air. So you're going to fire a shot of compressed air. That's going to produce a pressure wave in the water. And that pressure wave is eventually going to make it down onto the seafloor. And when it hits the seafloor, it's going to end up producing seismic waves as a byproduct. So when a seismic wave is moving through your sequence of rocks, it can do one of two things. So when a seismic wave comes to a boundary, it can be reflected and it will bounce back, or it can be refracted and it will change its angle. So if you remember all the way back to the first lab when we were talking about how seismic waves move through the Earth's interior, exactly the same thing will happen to the seismic waves as they move through our sequence of rocks. And so what geophysicists can do is they can detect these reflected and refracted waves, and they can use that information to produce a model of what is going on in the subsurface to explain the data that they collected. So as you can see, in this case, we have our seismic section here. And then below it, you can see there is an interpretation. So if you look here, we can see we have some kind of erosional surface, which is this red line. So we've got an unconformity there. And you can see that because it's such a highly irregular surface. Now, on top of that, you can see we then have a whole sequence of horizontally bedded rocks. And then we have another unconformity marked out here in green. And then we have another sequence of sedimentary rocks on top. Now, what you'll notice is this upper portion, okay, so anything above the red line, you can see the layers relatively clearly, and that's because there's a contrast in the physical properties between the layers. So as the seismic wave moves from a sandstone to a mudstone, or maybe from a mudstone to a limestone or something like that, the changes in the physical properties will affect how the wave is refracted. So that will lead to essentially bigger changes in what the seismic waves do. And so typically seismic sections are most efficient when you have layered strata, so like a sequence of sedimentary rocks, and there are differences in the physical properties of each of these layers. And that will lead to essentially the best quality image you can get, because you'll be able to pick out individual layers within the sequence. Now compare that, on the other hand, to what's going on down here in the lower portions of the seismic section. You can see you've lost resolution. It just looks mostly fuzzy. And that's because the rocks down here are probably more homogeneous in their composition. You could be moving down, for instance, into things like granite, which is a very homogeneous rock. And when seismic waves pass through a homogeneous rock, they just get scattered. So they go in all directions. And so this will result in very poor resolution, and you won't really be able to see what's going on. So these seismic sections are extremely helpful when you are looking at layers of sedimentary rock, which have different physical properties between the layers. And by taking this data that's produced, you get to produce what's referred to as a seismic section, which is the thing we can see at the top here. So your seismic section is a two-dimensional slice. You're just taking a slice through the sequence of rocks. But what you can do if you have powerful enough computers is you can take a whole load of these 2D slices and you can combine them together to produce a three-dimensional model. So you can see that seismic data is actually an extremely powerful tool when it comes to correlating stratigraphy. However, there is one issue. It is also very expensive. And so that's why the majority of seismic work is done by oil companies, because they have the money to be able to afford that kind of thing. Most of the time, your average geologist will not have access to the type of equipment that will allow you to produce this kind of information. So most of the time, if you're either a geophysicist and you're trying to correlate rocks between locations, you will typically use one of the borehole methods. So you use something like resistivity or spectral gamma. It's only if you are, if you're with an institution that has a large amount of money where you may consider doing something like producing seismic data. Okay, so this looks like a good place to stop. So please get up, have a walk around, get yourself a glass of water, and then come back for part 2.